page 18 then, this is a second example of a double replacement reaction in which we work through the overall TIE and NIE. And this will be a companion problem. Now, a similar case, write the overall reaction for the process between potassium iodide and sodium chloride, the TIE and the NIE. For the overall reaction, potassium iodide and sodium chloride are going to change partners. The changing partners part looks like this. Take the I minus and pair it with Na. Those are both ions. Pair the potassium with the chloride. Leave some space. Now if you go to your solubility rules and you look up anything with sodium is going to be soluble. Anything with chloride is going, almost anything with chloride, but anything with potassium is also soluble. Both of those are aqueous species. When we, before we move on, balance, everything is fine with a 1 coefficient. Now the TIE. TIE is going to have any strong electrolyte, which strong electrolytes are ionic compounds that dissolve, will break up into ions. Same thing for sodium chloride. Then we get to the product side. Sodium iodide, also strong electrolyte. Potassium chloride, also strong electrolyte. And when we do our spectator ions for NIE, we cross things out. Cross out K plus. Na plus, also a spectator. Exactly the same formula and charge on each side. Same thing for iodide. Same thing for chloride. There's nothing left. No reaction. And when I say no reaction, what I mean is there were no bonds made, there were no bonds broken when we poured these two test tubes or solutions together in any format. No reaction, no bonds formed, no bonds broken. And that's fine. That's where the result we wanted to get to. And in fact, if I show you a picture of this, it's like pouring two aqueous solutions together. Nothing to see here. Move along. Now let's pick up with our second subtype of reaction. Those are going to be double replacement acid-base reactions. So this is still under DR for double replacement. Neutralization of the acid and base produce products that are water and a salt. And so before we do this, let's take a brief minute or two or three to go over strong acids. Strong acids, there are 7 of them. Hydrochloric acid, hydrobromic, and hydroiodic acid. Nitric, sulfuric, chloric, and perchloric. Those are always the two I think of last. They're the least common in general chemistry. 7 strong acids. That's it. Memorize them, know them. There are thousands of weak acids. There are only 7 strong acids, so memorize them. Strong acids are strong electrolytes. And they break up 100% into ions. And the classic example, which I'll put up at the top here, you take HCl, it breaks up 100% into hydrogen ions and chloride ions. Strong acids are strong electrolytes. Please remember that. Weak acids, we said that weak acids break up less than 5%, so weak acids are weak electrolytes. So break up less than 5% into ions. And therefore are more than 95%, greater than 95% whole molecules. And so what we call the 95% part is the dominant species. And when we write total ionic and net ionic equations, we will write the dominant species. That's why in my previous slide it said weak electrolytes stay together, do not break them up into ions. That's because they don't break up into many ions at all, and it is not the dominant species. Okay, so weak acids, they are going to be whole molecules in TIE and NIE. All right, strong bases. Strong bases is a category that we limit in this course to the alkali metal hydroxides. Because those are the most common ones. Those are the ones you see in the lab, by far the most, certainly at this level as well. We are limiting ourselves. There are more strong bases that you will encounter in the more advanced chemistry classes, but we will limit it to these examples for now. And so as examples, you can take your periodic table, you can go down the alkali metals, lithium hydroxide, sodium hydroxide, potassium rubidium, and cesium hydroxide. Those are the only strong bases you will see. Lithium hydroxide, potassium hydroxide, ... And strong bases are strong electrolytes. They break up 100% into ions. Sodium hydroxide breaks up into sodium ions and hydroxide ions. Now, weak bases, there are also a lot of weak bases. Again, we are going to limit ourselves when we look at the bases. First off, you must know that ammonia is a weak base. Amines are also weak bases, but I'm going to put that in parentheses. Remember, parentheses means useful to know long term, but not on the exam. If there is an exam which has an amine on it, I will say the amine blah blah blah, comma, a weak base, comma, and then you'll know how to handle it. But I can't just put ammonia on there, NH3, and expect you to know it's a weak base. Weak bases are also weak electrolytes. And weak acids, B whole molecules, R whole molecules. I'm not sure how I got there before, but we're going to write R whole molecules. In TIE and NIE. So there's some good definitions we're going to use. Now let's look at a very typical acid-base reaction, a neutralization reaction. Hydrochloric acid plus sodium hydroxide. Now you may know the pattern for this, you may not, but regardless, it is a double replacement reaction. One of the products is sodium chloride. We know that's aqueous. Anything with sodium is aqueous. The other product is HOH, also known as H2O, and that is a liquid. And there's also a saying, acid plus base makes water plus salt, where salt is a general term that could refer to any ionic species that dissolves. This just so happens to be table salt. Okay, we do have a solid liquid gas, something that is not an aqueous strong electrolyte here, so there will be a reaction. Our TIE break strong electrolytes into ions. That is balanced, by the way. That's the stuff I always forget, or more often than I would like to admit, forget. But it is balanced. I'm imagining that all four of these reactant species in their respective beakers or test tubes are floating around with their hydration shells around them. Sodium and chloride become aqueous ions with their own hydration shells. Nothing changed for them, in fact. But H2O is a liquid, and when we go through and cancel out the things that are the same, our spectator ion sodium and our spectator ion chloride both drop out. We're left with hydrogen ion and hydroxide ion forming water. This is a chemical reaction, and for this chemical reaction, a covalent bond has formed. Okay. Now let's at least start the process for acetic acid. As we know, acetic acid is a weak acid. One of the way to write its formula, and the way I generally prefer, is as CH3COOH, proudly displaying its weak acid or organic acid or carboxylic acid group. Potassium hydroxide. That's aqueous. Now, the H right here is the acid H, the H that will form the H+. That's the positive ion, and it's in the back. And so that's one reason that these are a little weird. Now you have to take them and pair them with the negative ion on the other one. We recognize that this is an acid-base reaction, so here is where that saying of acid plus base goes to water plus salt helps us. We do get water, and we do get a salt. The salt will be whatever is left. I'll use a different color for this one this time. CH3COO is the acetate ion. It is negatively charged, as we would expect, positive and negative. K plus, we get potassium acetate. Oop, no charge there. I apologize. That's not a charge there. I crossed it out. And anything with potassium is soluble. All right. I think we're just going to work this whole example because it is a good example of a weak acid. Now, I know we broke this up into ions to figure out what our products are. We now have to remember that this is a weak acid. Weak acids, the dominant species in solution is whole molecules. And however, potassium hydroxide is a strong electrolyte. H2O. And now strong electrolyte here, K plus. And the acetate does break up into ions 100%. Remember, NIE, cross out anything that is exactly the same on both sides. Those are the spectator ions. The only thing that is exactly the same on both sides is going to be potassium ion. And write what's left. And we then ask the net ionic equation, hey, how you doing? And then we ask it, is this a reaction? Were bonds made? Were bonds broken? I'm going to suggest to you that both occurred in this reaction, which is pretty cool. So the covalent bond to the H plus was broken. So, and we haven't done Lewis structures or anything yet, so we won't actually draw Lewis structures. But I'm telling you, the covalent bond to H was broken. That H plus then formed a bond with hydroxide. So here, covalent bond formed to H formed. And so both bonds were made and broken in this example. This will be a companion problem. For the companion problem, you can look up, or I will tell you, that the formula for formic acid is HCOOH, where the H in the COOH group, this H right here, is going to be the acidic H, the H plus. And let's motor through this. Gas evolution reactions. These are the third double replacement type of reaction. One of the products is a gas as a result of the breakdown of one of the products. Let me give you two examples of how this happens. When you write a overall reaction, sometimes one of the products will be carbonic acid. That is a weak acid. It is still existing dominantly as whole molecules. However, this is a special case where it spontaneously breaks down into carbon dioxide gas and H2O liquid. And so anytime you form carbonic acid as a product, cross it out, write carbon dioxide and H2O. This, by the way, is the same reaction, the spontaneous breakdown of carbonic acid, that is mostly responsible for allowing carbonated beverages to be so bubbly and fizzy that they're releasing carbon dioxide gas. There is some carbon dioxide gas in there anyway, but a lot of it turns out is carbonic acid that as soon as you open up your carbonated beverage of choice, further produces gas spontaneously. There's another one, you don't see this as much. If you take sulfurous acid as a product of a reaction, it will make sulfur dioxide, gas, plus H2O. This one you, again, won't see as often, probably not going to see it on quizzes or exams, so I'm going to put parentheses around it. You are much more likely to see it on the homework. But we'll concentrate on the carbonic acid example. For example, as we work through this A here, if you take sodium bicarbonate and hydrochloric acid, I'm going to write the hydrochloric acid first. Sodium bicarbonate, we know it's aqueous, we know it's soluble because it's got sodium. Switch partners, this time we have, well, the Cl and the Na to make sodium chloride, and H plus and HCO3 minus. That is a weak acid. Ding, we remember because we just talked about it, but we will remember because we will do it as well, that this has to be replaced. And I'm going to write them the other way, I don't know why, by H2O plus carbon dioxide. Now we can do our TIE and our NIE. We have a liquid and a gas, they're going to stay together. We're going to have aqueous, aqueous, aqueous. All three of these are going to break up into ions, and that will allow us to complete our the rest of this problem as a companion problem. And this is an attempt to show these two solutions being poured together and creating bubbles. Those bubbles are the carbon dioxide. And an example of sodium sulfate and nitric acid. This too will be a companion problem.